So here's a vector. It is a stick with an arrow on one end. We refer to this vector as we use the letters U and V and W. We refer to this, I'm going to refer to this as vector V. It's a vector, and it's not a number. It's not a real number. It's a vector. And so when I refer to it as V, I use this notation to indicate that it's a vector V. The book will use a bold printed V, so I can't really bold this. So we use this notation for a vector V. That little vector symbol on top of it. Okay, a vector has what we call an initial point. Of course, where it started and where it ended here is a terminal point. What a vector is different than the real number, because a vector has sort of two properties. It has magnitude, and direction. And when we refer to the magnitude of the vector, another name for that is the length of the vector. By the way, another name is the norm. The norm of the vector. I rarely use that word norm, but you may see it, you can read it. The norm, or the length, or the magnitude of the vector is the length. And then there's a direction. And usually the direction is given by an angle. Usually it's given by an angle theta in standard position, I want to say. Do you know what I mean by standard position? Standard position of an angle is, let's see, from the positive x-axis measured counterclockwise. That's a 30-degree angle is from the positive x-axis measured counterclockwise 30 degrees, right? That's standard position. So, magnitude and direction. So, when we refer to the magnitude, the length of this vector is the magnitude. We use this kind of double absolute value notation. So the V refers to the vector V, which has magnitude and direction. The double bar with V inside is just the magnitude of the vector, just the length. Like any course, we start with a lot of notation and language, kind of. Maybe this is the angle here, again, measured from there, from standard position there. Here I am, I am a math teacher. This is a math class, and so we can just do math without ever relating it to the real world, which is kind of what I'm doing so far. But I like to relate it. I like the word problems. I like the connection with the physics. And so for a second here, let's talk about this. I mean, what we're learning about, this really is a new world of things called vectors. And so, what are they used for? What physical quantities do we use vectors for? And when it's not a vector, I call them just numbers or real numbers. That's those. Before we learned about vectors, we learned about we were always dealing with numbers or real numbers. Well, the word for that now is scalars. So scalars are these things that aren't vectors. What they are is they're numbers. And so what are some physical quantities for vectors? Listen, I'll tell you. This is kind of a funny one. This first one is displacement. Really it's just distance, but when you want to write distance as a vector, you call it displacement. Let's do another one. Velocity. Velocity is a vector. And what do we mean by that? Again, it means it has a magnitude and a direction. So if I tell you I'm driving 30 miles per hour, that's really not a velocity. If I say I'm driving 30 miles per hour in a direction northeast, then I've given you a magnitude and a direction, right? if I just say I'm driving 30 miles per hour, that's just a magnitude. That sort of falls on the scalar side. And as a matter of fact, the scalar analogy to velocity would be speed. And it's the magnitude of the velocity is what it is. Acceleration can be written as a vector. By the way, perhaps you recall this from physics. Displacement could be thought of as distance or displacement or position, and the derivative of position is velocity, and the derivative of velocity is acceleration. Oh, good. So those ideas that's chapter 12 for us. So I won't be doing that right away, but those are vectors in physics. And then the other big category of vectors is this, forces. And then, there's all kinds of different forces. There's frictional forces, air resistance, which is like a friction, air resistance, friction, forces. One of the most famous forces is weight. Right now, I'm pushing against the earth with a force of 190 pounds. And the earth is pushing back at me with a force of 190 pounds. I could draw that. Here's the earth, here's me. And I'm pushing it on the earth with a force, and it's pushing back at me with a force of, and we're both just in equilibrium at the moment. If I pushed a little harder, maybe I could get it to get out of orbit. No. Oh, by the way, I just went off the screen here, but that's not. So forces come in all, there's a lot of different kinds of forces. Weight is a force. Friction. Can you think of any others? Tension. Tension is a force. So what's not a vector? Mass, time, temperature. See, they just have, these have a magnitude and a direction. These just sort of have a kind of just a magnitude, just a number. Yes?
Would deviation from essential temperature be a vector?
I don't think so. That'd be like a change in the temperature?
Yeah.
Right. No. Although you could say, I got you, you could say it's positive or negative, maybe. Right.
So the scalar is just a quantity, and the vector is just has a magnitude and a direction.
Yeah, that's the thing. So these are just numbers, and these are magnitude and direction. And when I say numbers, maybe you could kind of say magnitude. I mean, that doesn't really apply to a number, I guess. But one number might be bigger than another number, so it is. I did say weight, and I just want to say one more thing. So, you know what weight is? Weight is mass times gravity. And so that's a scalar. Mass is a scalar, but it's multiplied by gravity, which is a vector, because gravity is an acceleration. Gravity is an acceleration. And so this is a mass times an acceleration. In fact, Newton said that's what forces are, mass times acceleration. So the acceleration is a force. You're multiplying it by a scalar. When you multiply a scalar times a vector, when you multiply a scalar times a vector, you get another vector. It's a force. Hang on a second, I'm sorry. Let's go back over here. If this is the vector v, watch, I'm going to multiply a scalar times a vector. Watch this. What would be half of v? This is a scalar times a vector. If this is a picture of v, can you guess what would be half of v?
Would it be half of the angle and half of the distance?
Well, good guess, yeah. But no. Actually, we don't change the angle at all. It's just the same vector, same angle, but half the distance. Yes, half the magnitude. So I would draw a parallel vector. I didn't do that great a job. I would try to draw a parallel vector and make it half its length. Right, here's a picture of, if that's V, then this is half of V. Too many arrows aren't good. When you're studying vectors, don't draw arrows. What about 2V? Can you draw 2V? Twice? Yeah, just same direction, which means parallel is really what that means. Draw a parallel vector twice as long. And that's what it means to multiply a scalar times a vector. When you multiply a scalar times a vector, it doesn't change its direction, but it does change its length. Try to make it twice as long. What about this one? Negative 3V. Any ideas about that one?
Would it change the direction?
Oh, I guess that's the, there you go. So what did I say? When you multiply a scalar times a vector, it doesn't change the direction. Oops. When you multiply by a negative scalar, it does change the direction, but it doesn't change the angle. It just totally makes it, and what the book uses the word, I've never heard this word before, anti-parallel. So it is parallel, but it is now pointing in the opposite direction. And oh, by the way, it's now 3 times as long. Right. Pointing in the opposite direction, 3 times as long. If you don't mind, roughly. Yeah, good. So we've learned a few things. How to multiply a scalar times a vector. Now I started with, let's get back to how we started originally. I said you have an initial point and a terminal point. So the homework starts with something like this. Here I am, I'm at the point 2, 5, and here's another point. 11, 2. So, can you make a vector out of that? And then your first question ought to be, well, which one's the initial point and which one's the terminal point? Because that would be a different vector. Anyway, let's make him the initial point and him the terminal point. So I want a vector that goes from the point 2, 5 to the point 11, 2. So that makes him the initial point and the terminal point. And there's sort of this catchphrase. If you're trying to make a vector out of a couple of points, you do terminal minus initial. Terminal point minus initial point. Or I like just the phrase terminal minus initial is how you can create a vector. The truth is, that's real common sense. You could have done this without me writing this little formula here. You probably would have said, how do you get from here to here? How does x change? X goes from 2 all the way over to 11. So you go 9 over and 3 down. Is that what's going on here? I mean, I could do the math. Terminal minus initial. The point 11, 2 minus the point 2, 5. This is kind of funny. You've probably never subtracted points. But what you get is 9 and negative 3. Now, what did I say? Move over to the right 9 and move down 3. Right. Well, that's positive 9 and negative 3. Now, watch this. This will be new to you. This will be the new notation. This vector, then, we write like this. We don't write the answer as a point. If it's a vector, we write it with this vector symbol. 9, negative 3. Look, it's almost like an ordered pair. It really is like an ordered pair. It is horizontal and vertical movement. It is an x component and a y component. What do we call, in a point, we call it the x coordinate and the y coordinate. Now I'm using the language x component and y component. And then I put it in these whatever you call it, this type of bracket. I don't even know what to call that little type vector symbol bracket here. You guys okay? So then can I draw that vector? I mean, I figured it out by trying to figure out. To go from here to here, I had to go over 9 and down 3. That's what that is. That's the vector v, by the way. That's the vector v. That's one way to write it. You haven't seen that yet today, but that's how you write the vector v. I love it. This is nice notation. I like this notation. It means go over 9 and down 3. What's a little funny, so then here's a picture of that vector. And then I can label it vector v, whatever, there it is. Yeah, I want to show you something. If I walked up to you and just said, hey, can you draw a picture of the vector 9, -3? Then just kind of forget that for a second. If somebody just says, let's draw a picture of the vector 9, -3, then what you do is you're in 2 dimensions. By the way, we're in the plane. We're in 2 dimensions today. You draw your XY plane, and guess what you do? You start at the origin. It's just kind of standard. You start at the origin, and you go over 9 and down 3. And then you draw a vector. Guess what? The vector 9, -3 terminates at the point 9, -3. Am I right? Although I want to make sure a point is not a vector, but they sure are similar in the sense that the vector 9, -3 terminates at the point 9, -3. But I don't want to say a vector is a point. I don't want to say that. A vector is a stick with an arrow on it, and a point's just a point. But wait a minute. So we draw him at the origin. We go over 9 and down 3. And here's a beautiful picture of him. That's also 9, -3. It's the same vector, too, by the way. I mean, I don't want to call him something else. If he's the vector 9, -3, that's what he is. So then what I'm stumbling into here, this is always kind of tough for me to explain, but is that when you talk about a vector 9, -3, it's kind of like a whole family of vectors. It's the whole family of guys that go over 9 and down 3, regardless of where they start. But we sort of represent him by this one. We sort of all decided that, well, when you want to draw him, just draw him from the origin. But in reality, this vector 9, he kind of represents everybody. I mean, this is not a different vector. We don't call this a different vector. I know he's got a different initial point. They all have different initial points. They all have different terminal points. But if they're going over 9 and down 3, it's the same vector. We call it the vector 9, -3. So a vector sort of represents a family of vectors in a certain sense. Good. Well, guess what then? Back to this. If we are talking about this vector, and we just drew a picture of him here, let me put it back up here. We went over 9, sorry, and we went down -3. You know what? I think I want his magnitude, which would be his length. And so we're about to kind of stumble into a formula here. Again, when we started today here, I said, here's a vector. It has magnitude and direction. And so I want to calculate those. What is his magnitude and what is his direction for this specific vector here? Well, guess what? If you go over 9 and down -3, this is just good old right triangle trigonometry here is all this is, right, you guys? And if you want, so it's just the hypotenuse. The magnitude of the vector is just the hypotenuse. It's very simple. It's the square root of the 9 squared plus the negative 3 squared. So what is it? It's 81 plus 9. 81 plus 9 is 90, the square root of 90. In a math class, we kind of prefer our exact answers. The square root of 90 is good for me. I guess you could simplify that. That's 9 times 10, so that's 3 square roots of 10. Do you agree? All right, so either way, to tell you the truth, I don't really care about that. I really do not like it approximated, though. I mean, math is, we like our pure exact math. But just for fun, that's approximately. You pick up a calculator and you approximate it, right? What is the square root of 90? 9 point something?
486.
9.486, okay. 9.5 maybe, right, whatever. In physics class, you would worry about that. You'd worry about significant digits, I suppose, and Cool. In math class, I never worry about significant digits. I'm always trying to, I don't count, I just try to be, I would really like to be as accurate as possible, as accurate as I am. So I leave it exact, but if I have to round it off, I would do 2 or 3 decimals, seems appropriate. I did one today. Okay, so what did I just do? I found his magnitude. Yeah, using kind of Pythagorean theorem, really, right? Right triangle, trig, Pythagorean theorem, right. What if I want his angle? Which is this direction angle here. Well, I think I would, again, pretend you didn't do the hypotenuse yet. You just got the 9 and the negative 3. If you have the 9, and you got this angle, I guess that's opposite and adjacent. If that's opposite and adjacent, you might recall that that's tangent of theta would be the opposite over the adjacent. You guys okay? That means if you really want theta, you have to do the tangent inverse of negative 1/3. I just reduced that. And then actually, if you wanted to leave this exact, you stop here. But I actually would like you to calculate that. So if your calculator is in, and I'd like it in degree mode, we don't need a radian here. So we might need, practice this a second. What's the tangent inverse of negative 1/3? Tangent inverse, of negative 1/3. Cool, oops. So I got a negative 0.32, I think I'm in radians. So I'm going to go to mode and switch myself into degrees, because I kind of want to know how many degrees it is. And I'm getting negative 18.4 degrees. So we found his magnitude and direction. Yeah, that's what we did. And by the way, you know angles. Angles are funny. Is there another name for that angle? So there's nothing wrong with calling it negative 18.4 degrees, measured in standard position. That's what a negative angle is. If you go clockwise from the x-axis. But we said, another name would be counterclockwise. Would be that name. I guess that would be.
341.6.
341.6. Positive 341.6. 360 minus that answer, right. Plus that answer, right. Okay. You guys can interrupt me and ask me questions anytime. How are we doing so far? I mean, it's...
Why did, this is probably ridiculously basic. Why did you need degrees mode?
I just prefer it. I mean...
Okay,
we can just get it. We all have a better feel for what an angle is in degree. I mean, like I said, the answer was 0.32. So that would have been 0.32 radians. Nobody really knows exactly what that is, except now you do. It's roughly 18 degrees. I mean, we just have a feel for what 18 and 30 and 50 and 60, and we have a feel for those numbers in degrees. So. for the purposes of this, we can have some degree answers. But they'll be rounded off answers. These will be approximately rounded off answers. You know, once you pick up a calculator, rounded this off. You know, so, you know, some math teachers, we can do things different ways. Different people do things different ways. What I did here was I did a real example. What I could have done is given you this formula in theory first. So hang on. So bear with me a second. I'm doing this second. In other words, if I have a vector v, and he has an x component and a y component, that's what you call that, and that means he went, you know, over x and up y or down y. I just randomly put this in quadrant 1. And then this is the angle theta, and then the length of this is the magnitude of v. I mean, you see me labeling all this? This is a right angle. So now, with this picture labeled like this, what did we just discover? That the magnitude of the vector is the hypotenuse of the triangle, which is this formula, basically, the square root of x squared plus y squared. So there's a formula. I started with an example and now got to the formula. We could have done it the other way, but you're with me, I guess. And then the formula for the angle would be the tangent inverse of y over x. So what did we just learn? This is kind of important. What we just learned, this is a couple formulas right off the bat that again, I don't give you. You should memorize this, although, again, you either memorize it as formulas, but you also understand it as basic right triangle trig. It's really nothing you memorize. You just kind of understand this, I think. But what is it? If I give you the components, listen, if I give you the components, can you find the magnitude and the direction angle? Yes. Yes. The other thing we do is the backwards version of that. And physics does that a lot in physics class. They say, given the magnitude and the direction angle, if you're given the length of the vector and the angle, can you find the x and y components? So watch what falls out of this picture here. If I talk about the cosine of theta, what would you say the cosine of theta is? The cosine of theta.
The x component?
The x over, it's adjacent over hypotenuse. So it would be x over that, there's the hypotenuse, the magnitude of v, right? And then if I multiply this up to the other side, then guess what x is? The magnitude of the vector multiplied by the cosine of the angle. That's the x component. Real popular topic in physics. By the way, what do you think the y component would be? I could draw it up here. I could write it up similarly, but it's probably the magnitude of the angle times the sine of the angle. The magnitude of the vector times the sine of the angle. So this is the given the magnitude and the angle, can you get the x and y components? Given the x and y components, can you get the magnitude and the angle? Yeah, you can. So you can work back and forth here. And it all kind of falls out of this picture. Go ahead, Zachary.
Doesn't that, what if x and y, the real x and y, if you will, were both 2 times larger than what you get using that? When you get the wrong x and y?
All right, hold on now. What was your question?
If you have, let's say you have...
But if you know the hypotenuse length and the angle,
yeah,
you'll get
the right x and y.
The right x and y. Right. If the magnitude was kind of unknown, there are many. Right. A longer magnitude would result at right. Right. If the magnitude was doubled, the x's and the y's would double. That's a similar triangle, I guess. Right. And the angle would remain the same. So no, there's no problems with this formula. Again, one more time, what did I say? I didn't write, maybe I should write these words, but what did I say? Given the x and y component, can you find the magnitude and direction angle? Given the magnitude and direction angle, can you find the x and y component? And now I wanted to say a cannon launches a projectile at an angle of 42 degrees with the horizontal with an initial velocity of 320 feet per second. Find the horizontal and vertical components of velocity. Now, this is not difficult at all. It sure has a lot of big words, though. Big words. The big words are scary sometimes. Big technical words. But boy, this is so easy. I mean, this is just, whatever. I could draw a little picture of this. What's going on? Apparently there's a cannon here at ground level. It didn't really say whether it was at ground level. It could be up on a cliff, I suppose. I guess that actually kind of doesn't matter. But anyway, it's going to launch this projectile, and it's going to do it at an angle of 42 degrees with the horizontal. And its initial velocity is a vector. Its initial velocity is a vector, and how long is that vector? 320. Right, that's the magnitude of it. That's his, right. The magnitude of this velocity vector is the speed, is the 320 feet per second. So what's going on here? I guess I've given you a magnitude and an angle, and I'm asking for the horizontal and vertical components. Again, the word components should make you think of the x and y components. That's all. It's a real easy question. And it comes down to this, huh? Yeah, this. Let's just do it. Yeah, x. So x would be 320 times the cosine of 42 degrees. I guess now you've got to be in degree mode. Y would be 320 times the sine of 42. And again, this is a problem. Once it's kind of more of a word problem or a physics problem. I talked about let's do our pure mathematics and let's not round anything off. Well, hang on. When you're doing this, we pick up a calculator. We do round things off here. It seems to make sense to me. But sometimes I argue with students. When do you want to round? When do you don't want to round? So I think it's obvious when you're kind of doing real problems, we'll just round these off. And anybody help me here? What are those numbers?
237.8063442.
All right, hold on. How about this 0.8?
For x, and then 214.1.
Okay, thank you. Therefore, I could write this vector as, if I wanted to write this vector, I could write it in component form. In a way, this vector is given it's given there, and I drew it there, and I gave you the magnitude and the angle. But let's write it in component form, which would be those numbers. Hey, does it surprise you that they're sort of similar numbers? I don't know, that's kind of a dumb question in a way. What I'm trying to say is, if this was at 45 degrees, the cosine and the sine of 45 degrees are the same, and the x and y components would be the same. It would be, maybe it's obvious, a 45-degree triangle, the opposite and the adjacent are the same. The x and y components would be the same. So anyway, it's close to 45, so they're close to the same. That's all. I just noted that. By the way, this is physics. Now, do you know what happens now? This projectile goes, it launches, it does this. Its velocity is always tangent to the curve. I'm getting ahead of myself now. The initial velocity vector was this one, but 2 or 3 seconds down the road, the velocity vector is tangent to the curve here. It looks a little different. But you know what is changing? Gravity is affecting it, right? Gravity is slowing it down, pulling it down. But gravity is not affecting, this is physics, gravity is not affecting the x component. So the x component is the horizontal component. Gravity only acts in a vertical downward direction. So it's only going to be, if you wanted to write some other vectors, 2 seconds later, 3 seconds later, 4 seconds later, they would all have 237.8 as their x component. This guy would be changing. Pretty cool. That's funny. That's a little ahead of myself. Sorry about that. Okay. Look at this. Here's a vector v, 5, 8. And here's a vector w, -3, 2. And now what I want to do is add these vectors. And when you add these vectors, I want to do v plus w. The answer, I can call anything. I'm going to call the answer R, capital R with a vector on it. When you add two vectors, you get a vector. I use the letter R because when we add two vectors, we often call the answer the resultant. So I just named it R for resultant. But that word resultant is the sum of two vectors. If someone says find the resultant, they mean add the vectors. They might not even say add the vectors, but if they say find the resultant, you're adding the two vectors. And so watch how easy this is. Maybe, I don't know if you know this. Here we go. Vector R is the resultant. I'm going to add these vectors. Do you know how to add vectors? Again, you're in this new world called vectors. You got new rules. So you can, but a lot of the times if you just guess, you'll probably get it. Guess what? You add vectors component-wise. You add the x component with the x component. You add the y component with the y component. It's the easiest thing in the world. So the answer is, you add the x's with the x's, you get 2. And you add the y's with the y's, and you get 10. And you're done. That's the result. What's cool, I think it's cool, is the way this is done graphically. Check this out. So the vector v is over 5 and up 8. I'm going to try to be kind of accurate there. If that's a 5, hang on. That's a 5. Okay, that's an 8. Okay, there's my 8. So there's 5. There's the vector 5, 8. The vector -3, 2. That would be -3 up 2. Okay. So there's a little picture of the vector v and a little picture of the vector w there. And now I want to add them, and I already did it. I added them. But I want to add them graphically. And the way you add them graphically is you take when I started today, I called this the initial point and the terminal point. Yeah, thank you. We also can call it the head and the tail. Now wait a minute. We could call that the head, and this the tail. I guess that makes sense. Like an earthworm, sometimes it's hard on an earthworm to tell which is the head or the tail. But for the vector, it shouldn't be too hard. There's the tail. When you add vectors, you can pick them up and move them, because keep in mind, remember what we said about, this vector -3, 2. I mean, there he is, but there's a whole family of vectors called -3, 2. I could draw them anywhere. Well, then here's what I can do. I can pick him up and put his tail on his head. Sorry. But I can do that. But that means pick him up, keep him the same length, keep him the same direction, try to keep him parallel, and try to just move him over here and put him, boy oh boy, I mean, it's kind of, I'd say that ain't bad. You know what I mean? What did I just do? I think I did V plus W. I put W on top of V. I put the tail of W on the head of V. What if I would have done W plus V? I did V plus W, but W plus V would have just been putting V on top of W, which would have been grabbing V and putting him on top of W. Guess what that puts you right there. See, it sort of forms this parallelogram. And the resultant is this. I should have another color. I did have another color. The resultant is from the original shared origin to the new endpoint. Now check it out. Is that 210? Dang, that's beautiful, isn't it? It worked. Looks like 210 to me. Over 2, up 10. Beautiful. That's the result. That's how you add vectors, visually, pictorially, maybe conceptually. This is what you're doing when you add vectors. When you have the actual components, you just, so you just do this. You may never think about this, but this is important. It's, again, back to physics for a second. It's kind of like forces, If this is a, this is old, ancient physics, but if this is an apple cart, and you have a mule pulling the apple cart in that direction, and a mule pulling the apple cart in that direction, you know what the result's going to be? The apple cart's going to move in this direction. That's what we just calculated. Right. Well, and put it in modern terms, let's see. You don't have mules and apple carts, but Volkswagen hit another Volkswagen at these various speeds. The result would be some terrible crash off into this direction. But it's the resultant of these two forces results in this force. It's like I'm adding these two forces and they end up heading off, and that's the resultant force. These two forces acting on a point results in this. Right, this is kind of the way we talk. Right. All right, I got 10 more minutes, and I want to show you something before we quit. Like I said, I think all this discussion will help you when you head to today's physics class. I kind of wish more people could have showed up today for this, but that's okay. You can have a slight advantage over them. So, have I taught you how to multiply a scalar times a vector, right? Well, actually, I haven't taught you that. Hang on. So what if I was multiplying 2 times the vector 5, 8? I forgot. I never taught you that. I did tell you what it means, though. What it means is it just makes it twice as long and keeps it in the same direction. But making it twice as long, then he alluded to the fact that making it twice as long would make the x twice as long and the y twice as long, which is actually, guess what? When you multiply a scalar times a vector, you get, that's how you do it. You sort of distribute it, you get 10, 16. And it is twice as long. Are you following me? All right, so a scalar times a vector, adding two vectors, we just stumbled into that. Later this chapter, I can teach you how to multiply two vectors, but that's coming up. I hope she won't do that today. But anyway, we'll get there. That's by the end of this week. We can multiply vectors. And there's actually two types of multiplication. There's a dot product and a cross product. So that's interesting. New world. A couple different ways to multiply vectors. Check this then out. If you look at this vector. Now, I guess this implies that you take a vector and you divide him by his own magnitude. Now, I haven't really taught you how to divide vectors. What do you mean? You haven't done dividing vectors. Well, I'm not dividing vectors because remember, magnitude is a scalar. Magnitude is a scalar. So what I'm really doing here is this scalar times the vector v. Is that? So let's do it with this particular guy here, this vector 5, 8. So if I took the vector 5, 8 and divided him by his magnitude, it would be the vector 5, 8 divided by his magnitude. His magnitude would be, can you tell me his magnitude, please? And, you know, I gave you a formula. You just new at this. I know you're brand new at this. There comes a point where it doesn't take too long. I do a quick Pythagorean theorem in my head. I do 25 plus 64, right? Is that what I did? And put a square root on it. 25 plus 64, 89? Square root of 89?
Yeah, 9.5.
Okay, approximately 9.5. I'm going to keep this exact. Square root of 89, if that's okay with you guys. So here he is, look, square root of 89. Now, hold on. What I just said was, though, that's the same as 1 over, I don't want to get you confused. First of all, you're Cal 3 students. I guess you should know this. Multiplication and division are the same thing. Division is just multiplying by the reciprocal. I didn't really mean they were the same thing, but I meant division is multiplication by the reciprocal. So when I said I didn't teach you how to divide, well, I did teach you how to multiply. So I'm multiplying by this. You know, there's really not much to do here, but I'll take it one more step. You get 5 over the square root of 89, and then 8 over the square root of 89. And whatever. What did we just do? Hang on, what did we do? When we multiply by a 2, what do? We make it twice as long? Right? We made it twice as long. So what did I just do? If you multiply by a 2, you make it twice as long. What if you multiply by a half? You shorten it. I guess you make it shorter because you make it half as long. So what did I do? I shortened this vector, didn't I? Didn't I? And how short did I make him? It's not really fair for me to try to pull this out of you. Listen to this. So what if it was 10 long, and then you multiplied by 1/10? How long would it be then?
1.
It'd be 1 long, right? So I think that's what I just did. How long was this guy? What was his magnitude? The square root of 89. And then you just divided by his own magnitude. So he was the square root of 89 long, and then you divided by the square root of 89. How long is this dude right here? 1. His magnitude is a 1. He's length 1. You could prove it if you go calculate his magnitude. But the truth is, anytime you take a vector and divide by his own magnitude, this is length 1. And if it's length 1, that's called a unit vector. And that has magnitude 1. And we do that. That's kind of a frequent thing to do. Calculate a unit vector. Make it a unit vector. You take this vector and make it a unit vector. I guess that's when you're just more concerned with his direction and not his length. You make it a unit vector of length 1. by dividing by his own magnitude. You guys okay with that? So you can take any vector and make him length 1, and he's a unit vector. Okay. I'm getting to where I wanted to get here. And then I'm going to quit in just a few minutes. I may take you just a couple minutes of overtime here, but I wanted to bring up the term unit vector, but and this is, you can take any vector and make him a unit vector like by doing this. By the way, now that you made him a unit vector, I'd hate to call him V anymore, right? What was V? V was the 5'8". Now that he's shorter than he was, I shouldn't call him V anymore. I mean, he's somebody new. And maybe you could call him U because he's a unit vector, but just because you see the letter U doesn't mean it's a unit vector. Are you with me? He's not V anymore. He's the unit vector version of V. But now, this is what I wanted to talk about real quick. There are these standard unit vectors. And they are this guy, the vector I. This is a little vector I. In physics, I think they'll use a hat. In fact, when they're unit vectors, they tend to put hats on them instead of the vector symbol. I'm trying to help share a little. The notation in math and physics gets a little different. In fact, in physics, magnitude is often done with just one absolute value instead of the double absolute value, sometimes in the physics class. But I is the standard unit vector in the x direction. Can you tell me what that is? I'll just tell you. I'm running out of time. 1, 0. He's the standard unit vector in the x direction. I mean, what is the name of the vector that goes 1 unit in the x direction? I. Or you could call him 1, 0, but you could call him, he has a special name called I. J is the standard unit vector in the y direction. Guess what he would be called? 0, 1. That's a 1. That's called J, the standard unit vector in the y direction, J. So this is another notation for vectors that confuses students. I don't want it to confuse you. Listen, but it's because this is all it is. Now watch. So I can talk about vectors using I and J notation. So I can talk about this vector. The vector 5i plus 3j. But I'm here to tell you, all it is 5 of those and 3 of those added together will be the resultant. All this is this. I mean, this I and J are kind of just placeholders. It's just another way of talking about vectors. And our book uses it, but it's just, to me, it's just a little bit more writing. So in class, I'm always doing this. I'm always doing this vector notation. But our book and the physics class often use this vector notation. And it tends to confuse students. This I is not the imaginary number I. No. It has nothing to do with, but students aren't sure what this I and J are. And it's just this. Now let me show you something, just to convince you. Watch this. So this is 5 times the vector 1, 0. It's kind of like a scalar, 5 times the vector 1, 0. This is 3 times the vector 0, 1. Okay, now let's play this game. Watch this. How do you multiply a scalar times a vector? You just distribute it through. So the vector 5i is actually 5 of those little, it's actually 5 times those guys. Here's I. It's 5 of those. It's this. It's 5, 0. What about the vector 3j? Well, it's really just the vector 0, 3. How do you add 2 vectors? Well, you put the head on the tail and you draw the resultant. Or you just add these components and what do you get? I mean, this is nothing fancy here, but I'm just trying to convince you that there's this ij standard unit vector notation, and I just want you to know it's the same as this, and it's easy, and there shouldn't be anything confusing about it, but it can get students sometimes to do it. So guess what? I'm finished. I think we did a decent job of getting through 11.1. You should start on some homework. It's fun. You'll learn some stuff. You'll run into some stuff maybe I didn't cover. I think I did a pretty good job. My homework list is good. You know, it's not really 1 through 120, all of them. It's kind of a long list, though. It's 1 and 5 and 13 and 17. But, I mean, I tried to be fairly minimal. I tried not to work you to death in my homework list. Yet I couldn't resist. I love a lot of problems, so it's sort of lengthy. But if you do it, you'll learn. You'll learn. I mean, that's where you really learn. Sitting here with me and watching me, you do pick up some things, but you really learn when you do it yourself. So, and get confused and ask questions. That's really learning. So, I'm going to hit off on this thing. Thank you for listening, and I'll see you Wednesday.